About iron carbon diagram. Right? So iron carbon means we know this is called steels, basically steels. So this is the iron carbon diagram, and you can see here there are eutectic phases systems, and again the eutectoid. So we'll discuss what is behind this, and again there are so many phases in iron carbon diagram. So inside iron carbon diagram you have iron and carbon, right? This is a binary system. Major alloy is major element is iron, and there are little bit percentage of carbon. So we are mixing those percentage of carbon with the iron, and here you can see this is the iron, and again this is the carbon. So they have different phases with mixing different kind of percentages, right? So here you can see some names: austenite, ferrite, pearlite, and again cast iron, pearlite and carbide, then pearlite and cementite. Likewise, those are the phases of steel, right? Those are names here: gamma, alpha, beta. Likewise, they have those names, but here we can identify those phases of iron carbon percentages, right? So today it is about introduction, what we have now today, and cooling curve for pure iron, definition of structures, and again iron carbon equilibrium sketch, then explanation and how it transform, growth, and about the microstructure and mechanical properties. Likewise, we are trying to understand today those things behind our iron carbon diagram. Right, first thing, the metal, what we know basically is iron, is a primary constituent of some of the most important ferrous alloys. That means steels and cast iron. Likewise, there are so many. We are mixing some of the elements with iron, right? But here, major thing is iron, and we mix carbon to this system. So ingot iron, which is almost a pure iron, right? You know, in the previous ages they have used this pure iron, right? Ingot iron, right? Then we are having those sources, and we melt it and use that to build some of these items. Like, if you know that in the past ages, they have pure iron chassis inside vehicles, pure iron, right? Today we are having some of the alloys, but previous cases we have pure iron, and they have those ingot iron, and they melt it and then use it to form these chassis. So fire drainage culverts, refrigerator cabinet, washing machine, roofing ducts, right? Those are some of the examples. But nowadays we do not have this kind of pure iron, right? Because pure iron have some kind of advantages and again disadvantages inside. So to reduce those disadvantages, they have used some of the alloys, some alloy part, to get some kind of advantages to that. So by adding alloying elements, especially carbon, its properties are varied for various application in engineering, right? That is why, because after mixing those carbon into the iron, they can develop some of the properties, right? So we'll discuss. So ingot iron following typical mechanical properties. Now you know what is called mechanical property of an element. Then tensile strength, elongation, Rockwell hardness. Those are the properties, right? And so this is the cooling curve of pure iron, right? Pure, there is no any alternatives inside. So in 2800 Fahrenheit, so that means it equalizes with 1538 degrees Celsius. So there is a point, right, where it gets liquid. Then it transferred into some of these structures. I think now you know. So if the liquid transferred to basically to solid. So here you have liquid. So below that you have the solid of pure iron. Then there is a phase called alpha delta BCC structure. So atomic structure is BCC, 1400 degrees Celsius, right? So if you cool down, yes. So this is the pure iron cooling curve. So I'll explain again. So this is the liquid phase, right? This is the solid phase. So if you increase the temperature up to 1538 degrees Celsius, the total pure iron solid converts to liquid. So that is the melting point. But inside the solid also there are some temperatures, right? So with the increasing of energy, they have changed their structure, right? So basically, you know what are the structures, atomic structures. You have body centered, simple cubic, phase centered. Likewise, we have several structures. So inside an element like iron, there are different structures also, right? So that also you can identify by increasing the temperature. So this is a pure solid iron. If you can increase up to 1400 degrees Celsius, the structure also change, right? So they have delta, gamma, alpha, they have nominate those names to that, right? And again, they have identified those structure changes, right, using some of the mechanical properties. So here, from the lower degree temperatures, it is stated with BCC, they call alpha, right? It is a magnetic alpha phase. So if you increase that into 770 degrees Celsius, it then converts to alpha, but it is non-magnetic. This is magnetic BCC, here non-magnetic BCC. There is a change of temperature. And again, if you change that one in 910, then alpha non-magnetic change to gamma non-magnetic, but it is phase centered. This is body centered. Now if you increase that into 910 degrees Celsius, it converts to gamma non-magnetic FCC. Again, if you change that into 1400 degrees Celsius, this gamma non-magnetic phase centered change to delta BCC magnetic, right? So likewise, inside this kind of temperatures, you have these atomic structure changes also, right? You can see cooling curve, and again you can turn this cooling curve into a phase diagram, right? I think I have shown you this is the phase diagram. Using this cooling curve, you can convert this into that phase diagram, right? So inside the cooling curve, you can see there are so many changes of the structure. So they have identified alpha, delta, magnetic, non-magnetic. Likewise, they have identified that. But without getting this alpha, gamma, and this one, they try to define some kind of names inside the structure. So they have given some names like austenite, ferrite, pearlite, cementite, martensite, lead-burite. Like those are the names that they have given to those structures in the equilibrium state, right? So today we are trying to develop our discussion under how to identify these structures, right? What are the properties behind that, right? Now you know all of these details. I think if I say to imagine a simple cubic structure, now you can actually imagine what is A, right? What is R? Then those numbers, C and numbers, like, right, packing factor. Those are now you can identify, right? That is why we already studied about that. So inside iron, right, there are structures, there are so many structures that I've said, BCC, FCC like. So here you can see the changes of structures. This is body centered cubic, this is face centered. You can see inside the face center, right, there is another atom is phase, right. This one placed inside the face centered structure, right. Here also you can see, right. So that change again, they actually develop a name, different name to that. Here you can see in a face centered cubic structure FCC, they have placed a atomic carbon here, right, one carbon atom. So they said that is called austenite, right. Then again pure body centered cubic structure they call ferrite. And again you can place a carbon inside this, they said that is martensite, right. Here you can identify and you can see there are different kind of places that they can identify to place carbon atom inside the iron structure, and they have developed some of the names to that also. Here you can see carbon percentage, 0, how those A and C, right, you know what is A. Now there is another length that they have developed C, right, due to the placing of carbon atom, right. They said that carbon percentage 0, then C is equal to A, that is this one, right, body centered cubic, that is ferrite. Then if you change your carbon percentage into 0.2, then your C and A is different. It is 288 and 2858. Likewise they change due to the placement of carbon atom, right. So that is why they have identified this structure change and nominate some of these names, ferrite, austenite, martensite. Likewise they have developed these names due to the placement of carbon element, carbon atom, right. So these are the microstructure change, microstructure identification through those microscopes, right. Austenite you can see, right, the face, and again pearlite how it changed, right, but same pure iron, but due to the addition of carbon atoms you can see how the structure changes, and this is pearlite, you can see how it changed, and again the ferrite, right, the difference in between those phases, but same iron is there, right, only thing is adding the carbon atom, right. So these are also some of the microstructures. This is austenite, the 500 lenses, right, 500 zooming, and this is ferrite, right, and pearlite, and right, again pearlite, that it is very zoom one, right. You can identify those faces, right. So we'll see what are the structures now. First one, ferrite, right. It is right here, ferrite, pure body centered cubic, known as alpha solid solution. They have name is alpha, but after they have given the name. So it is an interstitial solid solution of small amount of carbon dissolved in alpha BCC iron, right. So you saw it. Then stable form of iron below 912 degrees Celsius, below 912. The maximum solubility is 0.025% of carbon at 720 degrees Celsius, and it dissolves only 0.008% carbon at room temperature. So they have different temperatures. Here you can see maximum solubility is something called 0.25 under ferrite, right? So if you have ferrite, then you can go up to 0.025 carbon addition at temperature 723. But if you try to mix at room temperature, so here they said only 0.08 carbon percentage can dissolve at the ferrite. Then it is the softest structure that appears on the diagram, right? So there is a softest because there is no any involvement of carbon inside body centered structure. Then this is the kind of properties they have developed inside ferrite. The tensile strength is something 40,000 psi value. Then you can convert this into Pascal and kilopascal. What you use in the converters. The elongation 40% in 2 inches, right? Then hardness, local hardness is something higher than 0, C0 B90, right? This is a notation of the length and the hardness values. So this is the ferrite definition, right? How it changes the structures. Then pearlite, it is called eutectoid mixture containing 0.8 percentage of carbon and is formed at 723, very slow cooling. You need to do it very slowly. Then it's a very fine plate-like lamella mixture. Lamella means this kind of we call these arrangement. And they have parallel lines like this. Right? They actually one parallelic structure, and it is called lamella structure. Right? You can see ferrite and cementite, like the mixture of these two. Right? Cementite is this kind of snake-like element, and ferrite is the background, right? That is the pearlite, the mixture of ferrite and cementite, right? The white ferritic background or metric contains thin plates of cementite, that is dark, plates like those are ferrite and cementite. The background is ferrite, right? This is the properties, average properties. So if you have a pearlitic structure like this, so you can apply a tensile strength of 1200 psi. The previous case it is 40,000. So if you have this kind of lamella structure, your tensile strength will increase. Then elongation again 20%. Hardness, it is also high, right? Then austenite, this one is an interstitial solid solution, carbon dissolved in gamma, that is FCC, right? Then maximum solubility is 2% carbon at 1130 degrees Celsius, right? So if you want to find this austenite, you have to use 2% carbon at this one, at this temperature. So it is high formability. Most of heat treatments begin with the single phase. Austenitic is a single phase of FCC, right? So it is normally not stable at room temperature, but under certain conditions it is possible to obtain austenitic at room temperature, but you have to apply high pressure, right? So if you have a high pressuric background inside your container, so you can apply this austenitic phase at room temperature. Right here, the properties, tensile strength is something higher than pearlite, 1.5 lakhs psi. The elongation 10% in 2 inches, right? Then hardness also high. Then you have toughness, right? Hardness and toughness also something very high of the austenitic phase. Then cementite, what we call iron carbide, Fe3C, and carbide is very hard, brittle intermetallic compound of iron and carbon, right? Fe3C contains 6.67% of carbon. So it is the hardest structure that appears on the diagram. Exact melting point is unknown. So you can't actually do that melting without applying a pressure, right? So its crystal structure is we call orthorhombic. Now you know this structure, right? Simple structure. It is called orthorhombic. Low tensile strength approximate that is 5000 psi, but high compressive. Right? Your tensile is low, but is very compressive. You know the difference in between the tensile and the compressive, right? Think you have the experience with cast iron and steel, right? So cast iron as example, the engine cover of a machine, right? So they developed this one using some of the cast iron. So if you just use your hammer inside a cast iron and steel, you can see the difference, right? That is cementite. And again another structure called lediburite. It is the eutectic mixture of austenite and cementite, because they are actually formed during those temperature changes. So it called 4.3% carbon form at 1130, right? The previous case also you can see that is also nearly 1130. So simple changes due to the percentage of carbon. Right? You have austenite and cementite mixture. It is called a lediburite. Then martensite, a supersaturated solid solution of carbon in ferrite. It is formed and still is cooled so rapidly, right? That's also very important, because you can see in the previous cases you need to do that one slowly cooling, but here it is called rapid cooling, right? So your cooling and heating process also influence of this kind of changes of the structure. Austenite to pearlite suppressed. Then intersected carbon atom, this to the BCC ferrite into BCC tetragonal structure. It is called BCT, right? Body center tetragonal. So responsible for the hardness of quench seal. So quenching is something we call rapid cooling, right? So we'll discuss about those cooling and heating methods. So iron and iron carbon diagram, a map of the temperature at which different phase changes occur on very slow heating and cooling in relation to carbon is called iron carbon diagram, right? So you know, now we discuss about the cooling curve. You can change your cooling curve into a phase diagram, right? We'll discuss how it converts in the previous lectures. So iron carbon diagram shows the type of alloys formed under very slow cooling, proper heat treatment temperature, and how the properties of steel and cast iron can be radically changed by heat treatment. So heat treatment means you can do heating or you can do cooling, both. It is called heat treatment, right? So this is what we call the phase diagram, iron carbon phase diagram. There are various features, right? There are phases we call liquid, solid, and liquid solid mixture. Then we have solid mixture, right? So likewise we have different kind of features due to the change of structure. The liquid, you know the difference. Liquid means the melting. So if you increase the temperature up to melting point, so after that you have a solid and liquid mixture, then suddenly it is reached to a liquid temperature after the melting point. All of these elements go into the same temperature of melting point. So there are reactions. So at the pearlitic state, right, you have liquid plus delta, it converts to gamma. Then eutectic, you know, eutectic means is start with liquid and turn into solid. So here gamma plus carbide Fe3C. Then eutectoid, gamma also eutectoid means it is start with solid solution, and here gamma changes to alpha plus carbide and Fe3C, right? It changes into these two. Then delta, it is a BCC structure we call paramagnetic, right? Then alpha ferrite is a BCC structure, it is called ferromagnetic. Normally it is the ductile one, right? Ductile and brittle, you know the difference. A metal is a we call normally a ductile, right? But some stages with the difference of temperatures and the chemical composition, they convert into brittle, right? Brittle means like glass, it suddenly broke. But if you have ductile, you can see a plastic and elastic deformations, right? So after aging those plastic deformation, they suddenly broke, right? That is what we call ductile. But in a brittle, we do not have any plastic, only elastic and break. So maximum solubility carbon in ferrite is 0.22, and again austenite 2.11, right? So this is something we need to study when we go through the iron carbon diagram, right? Right. Three-phase reactions. There you have pearlite, eutectic, and eutectoid. So peritectic, eutectic, and eutectoid. Peritectic at right, thick means it is start with liquid and convert to solid. So toid means start with solid, it will change into liquid plus solid or only solid. So at 1490 degrees Celsius with low percentage of carbon, right, this peritectic can happen, right? But here peritectic, there is no value of finding peritectic using in engineering importance, but you can use it in some areas like making some alloys, right? Because that is also one of a kind of element that you use for formation of some alloys. So those are very important. That is what we need to just find it, right? Then eutectic at 1130 degrees Celsius with 4.3 weight percentage of carbon, that alloy called cast iron, right? That is the highest amount of carbon. Then if you add that amount into iron, it is called cast iron. It is a eutectic. Eutectic means start with liquid, change into solid. Then eutectoid at 723 degrees Celsius with eutectoid composition of 0.8 weight of carbon, two-phase mixture. It is ferrite and cementite, right? You know. So one solid converts to two different solids here, right? Peritectic, this is liquid plus delta, this is a solid, converts to solid gamma. Then eutectic, liquid changes to gamma plus this one and Fe3C. Then eutectoid is gamma changes to alpha for Fe3C, right? That is a change, right? This is the phase diagram reaction we call systems, right? So we have 5 systems. So out of 5 you have 3 here: eutectic, eutectic, and eutectoid. So how to read the iron carbon diagram? Right here, those are the changes. This is the eutectic phase. You can see liquid change into gamma plus Fe3C cementite, right? So this is a kind of system change, eutectic. Then eutectoid is also there, right? You can see gamma change into alpha plus cementite, like those are the changes you can see, right? That is how we read the iron carbon diagram. diagram. The diagram shows three horizontal lines which is indicate the isothermal reactions, cooling and heating. Those three, 1, 2 and 3. First horizontal line is at 1490, where peritectic reaction takes place. That means liquid plus delta converts into austenite, right here, this one, right? This is Fahrenheit degree Celsius. You can convert. So 1490 degree here, you can see it changes to this gamma, that is austenite phase. Then again second horizontal line at 1130, liquid change into austenite and cementite. This one, right? Liquid change into gamma austenite, right? And cementite Fe3C. Then third horizontal line at 723 degrees Celsius, where eutectoid reaction takes that austenite gamma change into pearlite, a mixture of ferrite and cementite, right here, this one. So this is 1490, this is 1130 and this is 723. Those are the three horizontal lines you can see here. And this is the gamma change into alpha plus cementite Fe3C plus alpha, right? This is the pearlite. So this is pearlite range, and this austenite, right? So this is liquid. Likewise, that is how we read the iron carbon diagram for our applications. And so major purpose is to how to use it for applications. So to identify the importance of using this one in application, first we need to look at how to read it, right? Those are the actually we call very important lines inside iron carbon diagram. So delta region of ferrite and iron carbide diagram, right? It is liquid plus delta, right? That is a delta region, and convert into ferrous carbide, that is austenite. So this is liquid, right? And this is liquid plus delta. This is the delta formation. So delta formation means you can see the difference of carbon element inside the iron, right here. The amount of carbon maximum one is 0.1. Weight percentage of carbon inside iron is 0.1. So up to that level you can go with delta. So after the temperature, it is 1490, this one here, right? The delta region converts into liquid plus delta. If you increase the temperature after this line, totally it converts to liquid, right? That is 1490 degrees Celsius. So in that one, you can see liquid plus delta, right? If you just cool, it converts to austenite of delta, right here. That difference, right? Delta, austenite, and again austenite. So if you just cool it after this line, it is austenite. If you heat up to this one, delta plus austenite, and after heating it is going to delta, right? That is how it change here. Then ferrite region of iron carbon diagram. This is 723 degrees Celsius, right? This is the austenite phase, right? This one. Then again austenite plus ferrite below 910. And if you just cool austenite plus ferrite, it changes into ferrite plus pearlite, right after 723 degrees Celsius. It is called ferrite region. Right. So this is something we call simplified one, because austenite change into ferrite plus cementite. So this is the austenite. This is the temperature 723. So austenite directly change into ferrite plus cementite after 723 degree. Total out of this, you can see under this line you have ferrite plus cementite, right? It is called pearlite. So total content of iron carbon is converted into ferrite plus cementite, we call pearlite, after 723 degrees Celsius, right? So this is the amount of carbon that you can apply, right? You can see here 0.02 line, then here 0.07, it's nearly 0.8, then 1%, then 2%. Likewise, you can increase. Maximum is 4.3. Right. This is how the structure changes with the temperature. So we'll discuss this one. Austenite goes to ferrite plus cementite. So here, this is the austenite phase. I think now you can understand it from the microstructure. Right. It is simply austenite. So if you just cool down below 720 degrees, you can see the pearlite change, right? Because in the previous one I have showed you. So this is austenite, right? Then this is the pearlite. So pearlite means you have two different ferrite and cementite. That is how it changes. Right, so by looking at the structure, you can guess what happened, right? Because if we change the temperature, you can see here the structure change. Right? So after changing the structure, you can see the mechanical and the properties also change. So that is what the importance of knowing. If you apply ferrous and iron and carbon diagram or an carbon mixture in application, if you just increase the temperature up to that level, or as example, if you just use an iron carbon mixture, right? So you don't know about this and you just mix iron 98 and 2% of carbon and make an alloy, right? Iron carbon alloy, and you use that one in a machine element, right? Like a gear wheel. So after some kind of rotations of the gear wheel inside the engine, or inside your some of the application, so temperature of this gear wheel is just increase by some amount, you know, that due to the this kind of forces apply on that, and again the friction, right? Then this kind of vibrations and all that happening to the gear wheel, and suddenly the temperature will increase. So after increasing the temperature, your mechanical properties of that same one will change. So due to that change, it will fail due to some actions, and because it will move into ductile to brittle, right? A simple example, I'll explain it, that you know the Titanic ship also failed due to the transition of this kind of phases or the structures. Okay, I have just explained about the structure changes, right? So if you just go along with this line, right, this is the 0.8% of carbon. Here you have above 723 degrees Celsius, you have austenite. So if you just cool it below 720 degrees Celsius, you have pearlite, right, plus cementite. Cementite very simply you can see, but that is also a mixture, right? That is a vertical line. Only here you have two phase changes, structure changes. But here you can see in this line, just here you have austenite. Then if you the carbon amount is 0.4, here 0.8, here 0.4. Austenite, so after this line you can see the change of that, that is austenite plus ferrite here, and below 723 you can see ferrite is there, and again pearlite, right? So that is how it changes with the vertical line. So if you go along with horizontal line, you can see the changes of carbon percentage. Here you can see 0.4 carbon and 0.8 carbon of the change occurs, right? So both you have to identify the same temperature also, due to the change of carbon percentage you can see the structure change, right? So here you can see cementite also form of above percentage of 1.2, right? So likewise, so if you change the temperature, definitely structure change. If you change the composition, then again structure change. So if the structure change, right, then it will happen with the mechanical properties also. So that change is the most important, because it will use in so many applications. So before use those elements in application, you have to identify these things. You have to make sure your process will lose something if you do not clearly view those, right? That is the importance of knowing phase diagrams, and how to read a phase diagram, and again how to identify a phase diagram, right? Because here most important thing is iron carbon, because so many applications are behind with the iron carbon, right? Because iron is the major metal in our past years, so they use iron so many applications. So after knowing the advantages and disadvantages, they change that, right? They already change that with the other metals also. As example, this vehicle chassis, right? So pure iron now changes to some alloys, and again the electric wires also, right? First they use steel, now convert to copper, right? So they identify the difference, now they change it, but at the first stage they use major metal as iron, right? Then the austenite to ferrite, and again cementite formation in relation to iron carbon dioxide. So in order to understand the transformation process, consider steel of the eutectoid composition. So before knowing these things, I will give you one advice. So try to draw this iron carbon diagram with your own effort, right? Because you have to imagine that diagram before using it, right? Just if you can imagine it, then these things will definitely go along with your concepts. So my first advice is to try to draw your iron carbon diagram in yourself, right? So then if you can just diagram vents. Iron carbon alloys of 2.11 carbon or more we call cast irons, right? The maximum or minimum is 2.11, maximum is 4.3. So typical composition 2 to 4 carbon, 0.5 to 3 silicon, less than 1% magnesium, and less than 0.2 sulfur. This is the typical composition. Silicon substitutes partially for carbon and promotes formation of graphite as the carbon rich component instead of Fe3C, right? So this is about cast iron. Applications use Taylor properties of steel and heat treatment about them, and it is also used to comparison of crystal structure of metallurgists in case of rupture. It is called fatigue, right? Fatigue failures, you have so many failures, right? At the fatigue failures, if you have is periodic forces apply, right? There are different forces that can apply onto a system or onto an item, right? You have constant force can apply long term. If not, you can change the force. It is called periodically. You can change amount of force. Then constant force can apply periodically, right? That is how the force application change. So that application of force also effect to the failures. So in the simplest form, steels are alloys of iron carbon. Phase diagram is a fairly complex, but we'll only consider the steel part of the diagram up to 7% carbon, right? You can go up to 7 or 8, but cast iron, and if you just say about the steel, it is rather it's up to 4.3 something, right? Here this one. Carbon solubility in iron. Solubility of carbon in iron is function. Yes. So carbon solubility of carbon in function is structure and temperature. There are so many changes. So these are the phases. Alpha ferrite. So there is a solid solution in carbon. BCC iron. So that structure is very important. So it is an interstitial solution of a small amount of carbon dissolved in alpha iron. BCC has relatively small interstitial positions. So body centered cubic means you don't have any kind of, if you know the R and A value, right, that amount is very less inside two atoms, right? But FCC, you have higher that C value. In the previous, I think now you can understand what is C and A. So C value is higher in FCC, not in BCC. So the maximum solubility is 0.022 at 723 carbon, and it dissolves only 0.008 carbon at room temperature. This is the amount. So in between you can change. So BCC has relatively small interstitial positions. So that amount will change. That means interstitial positions due to the structure change. So it is the surface structure that appears on the diagram. Transfers to FCC austenite at 912 Rigzel. So if you refer to diagram, you can easily understand what is the 0.022. So right here, this one, 0.022 changes. How we change? This is the alpha, it is called ferrite. Below 0.022 you can form it, but it says 0.008, right? 0.008 something near to this. Here this is not equal to 0. This line is the 0.00. You can I think here this one, right? This will not equal to 0. So this will start. This started from 008. Right, that is what it says. So transfer to FCC austenite at 912. 912 is here. This is the austenite. So after removing this one, this is again 0.08 and again 0.02. Total will reform above this line to austenite. Second austenite phase, solid solution carbon in FCC. Because here now we transfer to FCC, here BCC, right? Ferrite, BCC. The maximum solubility of carbon is 2.1 at 1147, right here. This change, right? This is austenite. Largest interstitial position FCC. Phase centered, you have higher C value. And transfers to BCC, delta ferrite at 1395 degree, at nearly like here, right? Delta will form after this temperature. It is not stable below the eutectic temperature unless cooled rapidly. Right, we can discuss that in next unit also. What is cooling, rapid cooling under this, right, 723 eutectic eutectoid. This is stick one, toid one. You can change that also. Right here, this is the austenite, interstitial solution of carbon in gamma ion. Austenite has FCC crystal structure, high solubility of carbon up to 2 point here. This is the 2.14, right, at 1147 degrees Celsius. After this one, you can't see austenite. It is a soft, ductile, malleable, and non-magnetic. Is austenite. So these properties are very important, right? So under this region, this region, right, only you can form austenite, right? Simply the temperatures are like 723 and this is 1493. Right, below this level you can form austenite. And again here carbon percent 2.14 below 0.08. In between this one gamma will form. Right, if not you can't form austenite. So austenite means it is very soft, ductile, soft, right, and malleable and non-magnetic. So if you want these properties, you have to control your process in between these levels. That is austenite. Then delta, it is ferrite. Solid solution in BCC. The same structure as alpha ferrite, right? Alpha delta, the name change due to the phase, that cooling curve change. Starting point I already mentioned. The stable only at high temperature above 1904 degree, above this one, right? You can see delta form, right? This is the delta. Melts at 1538 this level. So after this level you can see it will melt. Delta ferrite. This is alpha ferrite. This is delta ferrite. This is austenite. Then liquid solution here delta, solid solution of carbon and delta ion. The structure delta ferrite BCC, right, body centered cubic. BCC is there. Then 9 carbide called cementite. This intermetallic compound is metastable. It remains as a compound indefinitely at room temperature but decomposes slowly within several years into alpha ferrite, so alpha iron and graphite. It is typically hard and brittle interstitial compound of low tensile strength. Approximately 5000 psi. I think the mechanical properties basically I mentioned, but high compressive strength. So it is the hardest structure that appears on the diagram. You can see cementite is the hardest but brittle. Right, if you increase the hardness, then your brittleness goes increase, ductile decrease. Right, this is Fe3C. Intermetallic compound having fixed composition, orthorhombic crystal structure, 12 iron, 4 carbon, then hard and brittle. 12 means carbon 12, right. Then ferromagnetic up to 210 degrees Celsius. That is the cementite one. Right. So simple calculation. Right. You know how to apply the lever rule. Right here, we'll apply the lever rule. You need to find what is the amount, percentage of delta, point like here, right? Then this is, we have 0.55 carbon, this is 0.18, this is 0.1, right? if you want to find out the amount of delta, right, you can use the lever rule, right? So this amount and total, right? So if you want to find out this amount, right, this one, you can use lever rule. 0.55 minus 0.18, this means this length, divide by 0.55 minus 1, total 1, right? From the total 1, this amount, increase, multiply by 100, right? This amount is 82.2. So here you have delta up to 82.2. Then liquid percentage, then 0.18, 0.1 minus divide by 0.5, total 1. So this amount at this one, right, it is 17.8, right? So likewise you can use the lever rule and find the amount of those two, right? Then liquid plus delta, you can form austenite right here. Then eutectic and eutectoid reactions, those two, this also we'll discuss. And again, this here also you can apply lever rule and find, right? So you need the total and carbon diagram to use it, but here you can easily use it with the percentage values. So if you give those values, right, in this case, if you have the values, you can easily do it. So here also up to this point you can evaluate, right? But this one is very simply you can do it, right? This is the eutectoid reaction, right? Because here this is 6.7, up to that level you can go. So within these two, right, eutectoid means solid 1 forms solid 2 plus solid 3. Then austenite form into pearlite. Here you have 0.025 and this is 0.8, and next level is 6.67. So you can evaluate both two by 6.67 minus 0.8, that one from the total, and multiply by 100, right? So that calculation you can do. Simply the lever rule you can apply. That is eutectic reaction, ladybutyrite formation. Ladybutyrite means gamma plus cementite, right? Also you can apply, these are simply kind of calculations. So this is a summary of all, right? So now please memorize what we actually I can't actually explain total about first thing, about the systems. You have 5 systems, tick and toid. Then again temperatures, right? There are actually importance of 1490 and 1147 and 723, that is nearly 1130 also. So those are the temperatures. And again the points of carbon, 4.3 it is eutectic, then 0.1 peritectic, and again 0.8 it is eutectoid. Those are the regions here you can see. So below carbon percentage is called hypo, so above hyper. So here also you have hypo and hyper. And how to identify those phases: alpha, delta, austenite, cementite, pearlite. Those are the regions. So after finding those, you have to find out the mechanical properties behind those phases and the temperatures. Those are the importance of knowing. So total content behind the phase diagrams, about the iron carbon phase diagram I already mentioned.